Hi, this is recap lecture number 6, so thank you for listening. Today we're going to be reviewing slope fields and differential equations, and in particular focusing on how those topics are tested on the AP. As you recall, a slope field is a picture of what differential equations are trying to say. You have a lot of little baby tangent lines that are trying to show you the shape of the solution curves for a particular differential equation. And recall that when you solve a differential equation, if you're able to solve a differential equation, the solution is going to have a constant of integration in it. And that means that the solution to a differential equation is actually a family of curves, and that's why you have like a variety of different lines or curves that could be drawn through a slope field. Bear in mind that what determines the slope of these little mini tangent lines is the differential equation itself, because dy dx is itself a slope. And so if you have a point where the slope is equal to 2, that means that you're drawing a tangent line, a little itty bitty baby tangent line that has a slope of 2 because dy over dx is equal to 2 at that particular ordered pair. When the directions ask you to find the so-called solution curves, they are referring to the entities for which that differential equation is true. So the y equals whatever, for which the dy dx is equal to whatever they gave you in the first place. So the solution curves are those particular functions or relations for which the dy dx statement is true. Now, there was a stretch of years where there was always an AP free response question where you had to draw a little slope field picture like the one that I've included here. You know, they would have something like 6 or 12, 6, 8, 12 dots, and just say draw a little bit of the slope field. And sadly, that hasn't been so much present. That trend kind of evaporated as far as drawing the slope field. However, that doesn't mean slope fields aren't present on the test. I would just anticipate seeing them more in the multiple choice. However, in recent years, it has been a thing, it has been a trend that solving a differential equation is one part of the free response. At least the last few years, that has been the case. So definitely anticipate seeing that. Remember that the first step in solving any differential equation that you would see on the Calc AP test is going to be to separate the variables. And that is because the only kinds of differential equations that we have studied are those that are called separable differential equations. There are other kinds of differential equations that exist, but we have not yet studied them in this course, nor are we supposed to have. It is really helpful because of the separation of variables thing, to rewrite any y primes in Leibniz notation, like dy dx or dy dt if it's with reference to t, and make sure that you separate out that dx from the dy portion. Also bear in mind that as soon as you integrate, you have gained a constant of integration. And some of the student errors that I have seen in the past involve that plus c. As soon as you integrate, you have a plus c. And then if you have an initial condition that's noted in the problem somewhere, at time equals 0, this value is 6, the time to plug that in is right when you have the c for the first time. Then plug that in, find the value of c, and then worry about if you need to isolate for y or not. So for instance, if you were working a problem and this was the step that you had reached, and you're integrating both sides, you have your variables already separated, then in the next step, you'd integrate, and so that is the step in which you would get the plus c right then, not later on. And let's say that you were told there was initial condition of, let's make it simple, 0, 5. Okay, so then if you plug in 0 for x, you should get 5 for y. So if we did that, we would have ln of 5 equals 0, because that term is 0, plus c. So the constant is natural log of 5, which is an actual numeric value. And so then I come back to this stage in the game and I say, okay, well, that means natural log of y is x squared over 2 plus ln of 5. And then if the statement is saying, like, find f of x equal to y, or the y equal to f of x. That is them telling you, please isolate the y value, which we then could do rather easily. We'll make it an exponential. So we'd have e to the x squared over 2, and then it would be plus ln of 5 in the exponent, but I could also write that as times e to the ln of 5 equals y. And now y is isolated, and I could even tidy up if I was really wanting to, because this part, we could just think of that as the number 5. So 5e to the x squared over 2, all in the exponent, is equal to y. So notice the pattern there. We separated the variables, we integrated both sides, we gained a constant of integration, and then we didn't isolate the y at that juncture. What we did is we used the initial condition, signed c, and then worry about solving for y. All right, that's just a quick recap of that. I forgot to say in my introduction that we're also talking a little bit about area and volume. Okay, so I ask you here to draw 3 different pictures. A picture that represents the idea of top minus bottom relative to area, of splitting into different portions. Sometimes you need more than one integral, and also a picture that shows right minus left. So go ahead and pause the video and then come back once you have your 3 pictures drawn. Okay, welcome back. So here are my kind of floppy pictures. The first one is supposed to be showing top minus bottom, and so that's what I did here. Understand that when you are integrating just function f, you're getting this area. And when you integrate function g, you're getting this area. So if you subtract them, f minus g, the purple minus the black as far as what I shaded in, you're left with just that pocket of space up here. And that is actually what we're trying to find. So that's the setup, top minus bottom. If the top and the bottom switch places partway through, then you need to divide up the integral, or divide it up by several integrals, I should say. So the part from a to b, this part is this little pocket right in here. And then the part that is between b and c as x coordinates would be that part in here. Okay, so g is on top and f is on the bottom for that portion. So that's just to make sure that the signs turn out correctly. And you would have to do that for however many little pockets of space that you had. You would need to solve a system of equations or use your graphing calculator to find where the graphs intersect, so where your bounds should change. This next problem is one that you could do relative to x if you wanted to chop it up. But if you instead did the integral relative to the y coordinates, then you'll see that in this little pocket of space, kind of turn your head to the side, the red graph, or the f, is on top the entire time, the g is on the bottom the entire time, so you don't have to split into 2 integrals if you just think of both these as functions of y rather than functions of x. And so that's what my setup over here denotes. So I know that wouldn't be enough if you were learning this idea, just seeing those 3 little pictures, but hopefully that's enough to refresh your memory of some of the key ideas about area. And the next part, I point out kind of summary of solids of revolution. So when we studied volume, we said there are some things that are solids of revolution where the slices that you would take would be disks or circles. And there are some where instead of having a disk that's completely filled in, you have what's basically like a disk with a hole in it, and we call that a washer. And so remember that regardless of the shape, volume is found by integrating the cross-sectional area. And so if you're looking at disks as slices, your cross-sectional area is pi r squared. If you're looking at washers as cross-sections, you have big pi r squared minus little pi r squared. And then, just like the models that you guys made for class, the projected solids are those where the cross-section is a given shape. So there's a direction in which you can slice the thing so that you consistently get, say, triangles or semicircles or something like that. And again, volume is found by finding the cross-sectional area and integrating that. So regardless of what the shape is, you think about the area and then you integrate that area formula. Notice I wrote down kind of the variations. These are the different things we could ask, right? So if you have this, I could have a shape that is revolving around the x-axis, around the y-axis, around a different horizontal or a different vertical line. And that's true also of washers. And the variations of protected solids basically have to do with the shape. There is a technique called cylindrical shells, and we chose not to do that topic this year. Some other years I have done that topic. It just depends. But if you happen to learn that topic in some way, either studying it on your own or studying it with a friend from BC or something, you absolutely can feel free to use that on the AP test. However, there will not be any questions that require that as a technique because it's not technically on the AP content list. All right, we're up to the point where I need you to do a few questions. There are on the next few pages of your notes 3 multiple choice questions, so give those a try and then come back. You will notice that the first 2 are non-calculator and the third one says with calculator. Okay, I hope you had no troubles at all with trying those 3 multiple choice questions. So I'll show you my work for the first one. You can see that I started out with separating the variables. That's the step. Oops, sorry about that. That's that first step. We're going to separate the variables, then integrate both sides. That's where I get the constant of integration. Then right here, I'm substituting in this initial condition to find the constant of, or to find out the value of C. And I found out C was 7. And then I went back to the step where I first had the plus C and filled that in. And then this part was isolating for Y. And you might have had a hard time deciding if you should mark D or E. And honestly, that is a very tricky thing, but it comes from the initial condition right here. Oh my goodness. It comes from the initial condition up at the top. So I know that I want my solution curve to go through the point 3, negative 2. And it is the negative radical, not the positive radical, that would allow that to happen. So this is actually pretty important up at the top that they said 3, negative 2. Not just for finding C, but also for knowing which half of the relation, since it's not a function, it's a relation. Which part I want to keep. All right, this one is multiple choice, and I did this basically as a process of elimination kind of thing. And the one that I ended up picking is C. And the reason for that is when I looked at the slope equation here, which is what a differential equation is, I factored, and I noticed that I needed something where the slopes were 0 when x was negative 1. And then if you look up above at the picture of the slope field, right in here, you have this nice flattening out that's happening, and that matches exactly with this answer choice. None of the others have that attribute. So I didn't actually bother trying to solve any of these. I just kind of looked for key features, and I didn't go through all the key features on the other ones, but that's the one that matches up. And in question 3, I drew here what my calculator graph showed roughly. The numbers in black are the ordered pairs where the 2 graphs intersect. The numbers in green are the areas of those 2 little pockets of space. And then I added those together to get my final answer. All right, the tail end of your packet of notes has some free response questions. And I know that this is going to be long if you actually try all 3 of those. So what I would invite you to do is just take a look at each one. The first one here has to do with volume and projected solids, and you should do that if it's an area of weakness for you. The next one after that has to do, well, it's a differential equation problem, and so you're going to separate variables and solve for y in part B of the question. Part A is something a little bit different than that. You'll see. And the last one that I put in here is from the 2004 test. And this was in that stretch of time that I was mentioning at the beginning where drawing slope fields was like a big thing with College Board. So I would suggest that you do as many of these as you have time for. And if you don't have time to work all 3, because that would be a lot, and I understand that you might not, be selective. Okay, pick the one that is going to be the biggest area of weakness for you, so you would need the practice the most. I am going to, I would hope that you pause the video. I guess I don't have to pause in this case. Pause the video and then come back when you're ready to hear about answers. Okay, So if you did the 2011 B free response question number 3, this is the scoring rubric for it, and so I thought we would just go through that. Saves me a little bit of time writing, so I appreciate your understanding of that. So in the first part, you're asked to find the area of region R, and you can see here that they did an integral from 0 to 4 for the curved part. But then since function g was a linear function, they just used geometry there. You would also be, of course, you could do an integral from 4 to 6 for function g as well. It doesn't really matter. You should get 7 1/3 as your answer. And so you can see that if you were scoring yourself, you would get a point for setting up the integral, a point for having the antiderivative, and a point for having 7 1/3 as your answer. Hopefully that was straightforward. Then part B gets a little juicy because it says that the cross sections of the solid taken perpendicular to the y-axis are rectangles. We do need to set this up in a dy sort of situation. So your area should be from integral from 0 to 2, and then 2y times the difference between 6 minus y and y squared are going to give you the dimensions of the rectangle. So understand that in your picture, this function is x equals 6 minus y. And this function, when you solve for the other variable, is y, it's either y equals square root of x, or it's y squared. Oh my goodness, cannot write. Y squared equals x. When you isolate the x to have it in terms of y, those are the things that you need to use. That's where this integral setup is, and you get 2 points, say, for the integrand. So if you have some aspect of this, but not the whole thing right, give yourself a point. And then it says, write but do not evaluate that. Oh, that's weird. They say here answer. That surprises me because I guess I didn't look at the scoring rubric closely enough. Usually when they have integrand and answer, they give you 2 points for setting it up and 1 point for the answer. But in this case, it's just a sub in the first place. So I'm not really sure how the points would go in reality on this. Use your discretion. You're just scoring it for yourself. Okay. And then the last part is the classic write an equation of a tangent line. So you would need to find the slope. So the slope of g is -1, which means the perpendicular slope is +1. And then you need to find f prime. And so here's the derivative. And you need to figure out the ordered pair, right? Because you need a point and a slope to write the equation of the line. And so you substitute in and you get that the x-coordinate is 1/4, where the slope is 1. And so this gives you your ordered pair. So it's kind of a twist on the tangent line question. It's asking for the point of tangency instead of for the line of tangency, but hopefully you got that. It's just a little twist. Okay, this one is from the 2003 Form B version of the test. And the first part is really, I hope, very straightforward. I mean, it's kind of messy because the function is messy, but you find the second derivative by taking the derivative of this guy. And taking the derivative of that guy is just going to involve product rule with chain rule, and you need to leave things symbolically, and then at the end you're going to plug in that 3. So you can see here, they're finding the second derivative using product and chain rule, and then they tidied that up. And when you substitute in, you get 9 1/2 or 19 halves for the slope, the second derivative value at 3. Part B is solving a differential equation. And one thing I want to point out is look at how many points there are for this. Holy cow, it's unbelievable. So just a ton of points. And that has been the case in a lot of questions where you're solving a differential equation. It's just like, it's a ton of points on this one thing. So I don't know if that will be the case this year, obviously, but I would just be really good at this skill if I were taking the test. So separating the variables is a point, antiderivative of each side, and remembering plus c. Up to there, look, you already are up to 4 points if you can just get to that stage. Then we are going to substitute in our value to find the constant of integration, which is 5 1/2. Then you go back and try to isolate the y, okay? So notice that the solving for y, which I think is something that sometimes people struggle with that a little bit, just algebra, but still have a little bit of a struggle. That's just one point. And so I think that if you get to that stage and you're not really sure of like how to isolate the y, that might be something to jettison and just give that time to another problem where you have more luck. All right, question 6 from the 2004 test is one of those from, like I said, the arrow where they had you drawing slope fields a whole bunch. So this would be the picture that you would have gained just by plugging in different values into the differential equation, plugging in different ordered pairs, and being aware of things like patterns. So for instance, noticing, okay, every time y is equal to 1, I'm going to get a slope of 0. Allows me to do those 3 points split, lickety split, okay? Part B said, describe the points where the slopes are positive. That's going to be easier after you draw the slope field and have some sense of what's happening. So if x isn't 0 and y is bigger than 1, all of these points you see are tilting upward, not these, right? Because that's where x is 0, but the other places, and then the places that are beyond this as well. Understand they just had you do a teeny little chunk of the slope field. The plane keeps going forever. Then in part C, you are solving a differential equation. So again, the same kind of insane 6 points for this. And you can see here the solution for it. Okay, so hopefully this is what you got. Understand that they're using K because they're trying to know the difference between C and the K, because they found a constant of integration, then they had e to the C, and they can't call e to the C C because that's not true. That's where that capital K comes from. It's just a different thing. We might use a C star or a C prime or something like that to denote the difference. All right, so I hope that that was helpful. You can expect to see some free response questions using the idea of slope fields, differential equations, area, and volume. See you in class.